Good afternoon. I'm Bob Segi. I'm the co-director of community stakeholder engagement at the Tufts CTSI. And we're joined today by Brian Anthony from MIT. MIT is one of the 41 partner institutions at the MIT CTSI, and one in which we've had increasingly close collaborations. So it's really a pleasure to invite Brian to talk to us today about non-contact socially distanced vital signs and medical measurement. By way of introduction, Brian is the director of the Device Realization Lab at MIT. He's also a principal research scientist in the mechanical engineering department at MIT and an associate research scientist at MIT's Institute of Medical Engineering Science. MIT has been on the forefront of many of the devices that we've come to know and love in medicine, including many cardiac pacemakers and defibrillators have been tested at MIT. So they've really been in the medical business for a long time. You can look at his website for an introduction to Brian. I just would like to point out that I believe that he's the first speaker on our series, hosted by the Tufts CTSI, the Harvard CTSI, the University of Massachusetts CTSI, and the Boston University CTSI, who has ever won an Emmy Award. So we're now setting the bar high, and we're looking for future Emmy Award winning speakers to bring science to us as part of our strategy from all four CTSIs to bring research to the communities that we serve. With that, and I'd like to turn it over to Brian now to lead the discussion.
Bob, thank you very much. And just maybe a little bit more context for where the Emmy came from. I've been back at MIT since 2005. Prior to that, I started and sold a video instrumentation company. So we made high-speed video cameras and systems to control and configure high-speed video cameras. We ended up using that technology to on the PGA Tour as part of with CBS, and captured golf swings and club golf ball interactions, and made basically a video-based radar gun that could track the linear velocity of the club, the ball, the backspin of the ball. And for that, I won a technical Emmy. So there's lots of Nobel Prizes at MIT, but only one or two Emmys that I'm aware of. So today, I have a bunch of slides to share with you, but just maybe some additional background. I think in some of the conversations that I had with Bob and Maggie and reaching out to the community, I think it's important to sort of not only share these wonderful credentials being at MIT and winning an Emmy, but my personal background. Yeah, I'm a first generation college graduate, and in my family growing up, I was one of three children from a divorced family, and you went through a lot of sort of personal struggles to get to the point where we are now. So I want to make sure that as we have a broad segment of the community that could be listening here, that it's not sort of a preordained rite of birth where you're going to end up in what you do for your academics or for your career. And I like to sometimes think, and when I relate to my students, that recognizing the journey and the transformation that education has had for me and for my life, hopefully I can inspire others to sort of take risks and learn and develop their interests and try to do the things that they strive to do. So with that, what I want to share with you today from a technology background is maybe a journey that starts with COVID and then ends up someplace very different than COVID. So the title here is Non-Contact Vital Signs Measurement. And the agenda of things that I want to get through is give you a little bit of an overview of what we're doing at MIT to support the new challenges associated with COVID. Talk a little bit about non-contact body temperature measurement and use that to then talk about vital signs broadly, how they're currently collected. Use that to then talk about non-contact vital signs. And then what does it mean to go and move beyond our standard vital signs? So that's the journey that we'll try to rapidly go on today. And please ask questions as we go. Feel free to interrupt. I think in this COVID era, it's important to try to contextualize where we're all coming from. So this is the the Google map of Boston. MIT Medical is sitting where this little red dot is. We zoom in a little bit further. We can see the MIT Medical building. That's building E23 sitting here, and building E25 sitting right next to it. And you're taking a photograph. That's where I would normally be sitting, where one of my labs is, in this building over here to the left. And that's IMES, that's the Institute for Medical Engineering and Science. And to the right here is the entrance to MIT Medical. Now, if we take a few steps back, this is another view, and you can see walking down the sidewalk here, you would enter MIT Medical. And this is the way that this place looked before COVID. With COVID, we've planted 2 trailers outside of MIT Medical. And these trailers are designed to support our needs for testing the community, to make sure that people are symptoms free and COVID free, and to, in a very operationally robust way, have all of our community members that are coming back to campus. Not everybody wants to, not everybody has to, but for people that choose to come back to campus, with some frequency, they will be tested, and they will be sort of indicated whether or not they are, if they have COVID. The way that we're doing this is with these 2 trailers. The trailer on the right is what I'll call our swabbing trailer. So inside of this trailer are 6 stations where we have clinicians sitting basically behind a walled box, and we have people that will queue through this building, once every 30 seconds, and they'll be nasal swabbed. And that swabbing will then be tested, and within 24 hours, we'll have the report back on whether or not they have COVID. But prior to going into this swabbing trailer, we have this, what I'll call the thermal trailer, or the vital signs trailer. And what we want to do with this trailer is use it to prevent anybody that potentially has symptoms from going into the swabbing trailer. We really expect everybody to be negative going through the swabbing trailer. And so if we go through this vital signs trailer, we measure their vital signs. In this case, we're starting with just temperature. And if they have an elevated temperature, they would, from a non-contact measurement, they would then be routed to a clinician to have some discussion, to have a secondary temperature measurement. And if they are, if they're not having a elevated temperature, then they would go to the swabbing trailer. But if they do, then they would go routing. If we suspect that they have symptoms that would be indicative of COVID, they would go through a different routing, so to keep our clinicians and our community safe. So that was a sort of a high level. We have this operational plan in place to test our community that's on campus multiple times per week, both looking at their vital signs and doing viral testing. Today, I'm going to focus really on the vital signs, which is where a lot of my expertise and a lot of my research is. So this is the trailer that we're focusing on. People will go inside this door on the left, and they'll come out the door on the right, and then magic is happening inside of this trailer. But the magic is pretty simple. If you've ever come back on an international flight, and for many countries, they'll have external body temperature thermal cameras that will be monitoring people as they walk through. And so that's what we've deployed here, a very simple way to measure our body temperature. And this is a thermal image with somebody wearing a mask, and it allows us to get a reasonable measurement of what the external body temperature is by pretending that the body is a black body source and has a particular way of radiating light. But it will give a temperature reading that's about 2 degrees off of what your internal body temperature will be. That 2 degrees is a very predictable 2 degrees delta. We can use this as a non-contact way to measure temperature. And so what this looks like with somebody wearing a mask and breathing, this is a video, hopefully it's coming through clearly, of somebody breathing. We would use this camera system, this thermal imaging system, to not, in this case, we could extract the respiration rate, but what we do is instead we identify where their eyes are, and we take the temperature measurement from the tear duct of the individual's eye. Now, okay, what does this look like in detail? As we go through these slides, I'm going to walk you through the trailer and look at the technology. So this is a top-down view of the trailer. There's a queue, a line of people that come out and line up in front of the door. These little red spots are the places where they will stand, with the 6-foot social distancing. So this is the 2 red dots before they enter. Once they enter, they stand in front of a little camera station here. They get a measurement, and then once cleared, they go on. If they're cleared to pass through, they walk out the door. If they need to have a secondary check, they then go talk to a clinician that's staffing this. What this technology looks like, there's a rack system, a computer monitor with some structure to hold the camera, to hold some calibration sources. And this is what it looks like as it was being built in one of my graduate students' apartments. And the components are these mechanical structures, these cameras, and you get this image. There's some software that needs to tie all of this together. We need to detect where the eyes are. We need to detect where the corner of the eye is, because the tear duct is the most robust place to make these measurements. Inside of the trailer, this is what the system looks like. It's just a computer with a camera and a display. And if we just play the video, this is Ivan, who's one of the graduate students that's been working to deploy the system. What you saw him do is take his MIT ID, go up to the system, scan his ID, and he stands against the wall. Behind him is what's called a black body reference. So that provides a calibration source. And after he stood there for 10 to 15 seconds, depending on how long, how many multiple measurements we want to take, he'll get either a green light that says he does not have an elevated body temperature, or he'll get a red light that indicates that he needs to go and talk to the clinician that will be sitting over here on the opposite end of the trailer. Okay, so this is all very standard stuff. These are technologies that you will find in airports. They're technologies that you may find in your office buildings to measure external body temperature. And we did this very rapidly and put it inside of these trailers to support the operational needs for helping MIT to do testing and tracking of our on-campus population. But I want to expand the conversation a little bit. As I said, starting with COVID, let's build from there and share a little bit of the research that we're doing that allowed us to very rapidly deploy the system. So our vital signs. The standard ones that you can think of are our body temperature, our heart rate, our breathing rate, and blood pressure. And there are normal bounds that you expect for populations of adults and children. And we use those vital signs in monitoring our health, in monitoring our wellness, in diagnosing various diseases. Now, if you go to the doctor, you go see your clinician, they're typically going to be having a lot of contact with you, physical contact, both for palpation and understanding what's going on with you and having that human touch, but they're putting a lot of devices on you. And that could be electrocardiograms, putting sensors on your chest to measure your heart signals. And from those signals, you can get your breathing rate and your respiration rate. There's also, I'm sure most of you have had your pulse ox measured. And that's that little thing, little clamp they put on the end of your finger that glows red. And it's putting two wavelengths of light into your body and looking at the relative absorption of different wavelengths of light in your oxygenated and deoxygenated blood to determine what is your level of oxygenation. And that is another sort of vital sign signal that tells you what is the level of oxygen in your blood. There are other contact sensing techniques where you can look at air sensing and how people are breathing, and you can extract sort of your quality of your breath in terms of the chemical composition of what you're breathing, but also your breathing rate can be extracted. And there are many other techniques such as chest wall displacements or blood pressure sensing. Right? All of these are sort of the standard things that you expect, and you still will have these measurements done when you go to see the doctor. And these are made episodically when you go to the doctor. And some of these things, like heart rate and respiration rate, are available on wearable health and wellness monitors like a Fitbit or an Apple Watch or Garmin. Now, the questions that I want to ask, though, is how do we, in this COVID era, or in scenarios where you may not be able to make contact with an individual, or in applications such as in the home. If we want to measure vital signs, if we want to have some measures of physical health where we don't require contact, how do we do that? And what does that really mean? So vital signs, non-contact. What are the techniques? What are the ways that we can imagine making non-contact measurements on a person? And we can certainly look at a person. You know, optically, we've used a thermal camera, and we saw when they were breathing, we saw through the mask at least, we could see that temperature variation. So we could look at how that variation in temperature of the mask says something about how they're breathing. You could also use that with a different configuration of camera to look at the natural flushing of your skin, how the color of your face changes as your blood is pulsating through your face. A sound, you can listen to how somebody's breathing. Or if I'm doing ultrasound imaging, I use sound to image inside of the body. Or if I treat the body as a velocity source, meaning it's moving around the same way that you can be driving down the road and the police officer sitting at the side of the road has a radar gun pointing at you to measure your velocity. If I point a radar gun or something like a radar transmitter and receiver at you, I can detect motion. I can detect how your body or parts of your body are moving. So we look at how we use these different types of technologies to make non-contact measurements of people. So let's start a little bit with radar. With radar, again, it's very much analogous to what a radar gun gives you, or would give a police officer, tracking your speed as you go down the road. And you can skip the various sort of methods, but there are various ways of exciting a radar signal. You can make continuous waves. You can pulse the signals, but in the end, what you're really doing is you're bouncing a radar signal off of a person, and that person, as they move, changes how that signal is then reflected, and that reflected signal is then analyzed, and I can look at how that radar signal bounces off of somebody and extract quite robustly their breathing rate or their respiration rate. And I have these different modes, these different ways of either using a continuous wave or frequency modulating the wave or pulsing it. And these different methods have different levels of sensitivity to be able to extract breathing rate and respiration rate. But you can get, in a very robust non-contact way, these vital signs, like sort of the conventional vital signs that you would typically think of getting in a contact way. Here is what a basic in the lab demo looks like, right? So we have somebody sitting here, we have a little radar source sitting in front of them, we bounce it off of their chest, and we get back a signature that tells us something is moving at around 20 beats per minute, and that corresponds to the breath rate. We have some other things here that are moving around 60 for this subject B and around 80 for subject C, that corresponds to their heart rate. So we're not making contact with the person, a very robust non-contact way to get vital signs measurements. So that's radar. So let's look at what we can do with optical techniques. Now, optical spans everything from using a camera, analogous to what we did with the thermal camera, to using lasers that are both eye and skin safe. So how can a laser be used to make measurements from the body? If we shine a continuous wave laser, so something that is a continuous beam of light, not a pulsed beam of light, and we bounce that off of, or reflect that off of somebody's body, that reflection, that your body acting as a mirror, changes how that light is reflecting, changes the phase of how that light is reflecting. Now, if I have a very sensitive detector and very sensitive clock sources, I can look at how that light is reflected and how the motion of my chest or the motion of my neck or the motion of my face is modulating, is modifying that reflection to extract signals. Now, that's very analogous to what we did with radar. In all these cases, if it's an active interrogation, we generate some energy, RF, radar, or optical. We bounce that off the body. The body serves as some mirror, some reflecting source. And the way that our body, the way that our mirror is moving, will change how those signals are modulating to allow us to extract how our body is moving. And our body moves according to our vital signs, to our heart rate and to our respiration rate, to how we breathe and how we move. So this is just some raw data that is looking at the velocity of the chest that allows us to calculate the displacement of the chest. And then embedded in this signal is information about how we're breathing, our breathing rate, and our respiration rate. Now we can do that both on the chest, but we can now look at aiming such laser beams on various parts of the body. And just as a slide to sort of summarize a large breadth of literature where people have looked at everything from characterizing muscle tension to tremor, shake of the hand, or pulse, or heart, or respiration, or voice in a non-contact way using optical techniques. So now let's try to connect a couple of these things together to share with you how we're using these things, both as research questions to develop the robust ways to measure in a non-contact fashion heart rate and respiration rate and other vital signs, but how are we potentially connecting that to maybe some COVID needs? So we're hypothesizing that for a future operational need for whether it be at MIT's campus or other office buildings, there may be a desire to be able to, in a non-contact way, and probably every day, to monitor your body temperature, your heart rate, and your respiration rate. Now you could certainly do this. You can imagine doing this with wearable devices, or some aspects of this. So we're not saying that this is a replacement necessarily for wearables, but an augmentation. Not everybody wants to wear a device. So we hypothesize that having such kiosks, self-service kiosks, could be very valuable in supporting various workplace needs to make it easy for individuals to know that they don't have symptoms or signals, vital signs, that are different from their own baseline, or that are maybe indicative of them starting to have the flu or have COVID. So this is our hypothesis. And so we're developing this kiosk, or this chamber, so that we could use it operationally on campus, or maybe such technology could be deployed in the future waiting room of the hospital or of your doctor's office, where instead of just waiting to go see the doctor while you're next in line, you could already get the measurement of some of your vitals very rapidly out of the way. So we've played around with different structures of what these chambers could look like. And in the end, this is the sketch, if you will, of a system that we're currently building that will combine thermal, and it will combine optical and RF techniques to measure external body temperature, heart rate, and respiration rate. And this is what the system looks like. And this is a little bit about what the control system looks like. So we have thermal cameras that can give you the body temperature. We have this black body source, which allows us to have a reference. We may need to calibrate for the environment, for knowing what the temperature is, the humidity. And then we have the RF sensors placed in various ways, both above the person, in front of the person, and beside the person, that allow us to, again, use the body as a mirror and reflect radar signals off of them so that we can extract radar signals or extract heart rate and respiration rate. So this is, the various, some of the details on this chamber, on this kiosk, where we have to take into account the mechanical structure, the sensors, how we control and configure all the sensors, and also very concerned with making sure that we validate and to compare the measurements that we get from these non-contact measurements with conventional clinical grade wearable or contact sensors. So just as a point of reference, what does some of the raw data look like? This is at the top, we have reference signals, what a person's respiration rate is and what their heart rate is with a wearable device. And then what we're looking at in the bottom two plots are two different views of radar sensors, one a side view and one the top view. And what we're noticing is if we drill into these, we can detect, first of all, when somebody is present or not present in the system. So that's a helpful thing to do to automate when you start to make a measurement. But then if you drill into it, depending on the orientation of the sensor, in some places it's easier to detect respiration, whether when when you're using your chest as a mirror, with a sensor that's right in front of you, and instead of maybe a top-down view bouncing off the top of your head. Right? So you're going to see more of a respiration signal from your chest than you are going to be seeing that respiration signal from your face or from your head. So having a variety of sensors configured in different ways allows you to analyze the data and extract these vital signs measurements that you're interested in. Okay, so this is sort of an active research project that we're using to understand how can we develop these little self-service kiosks to very rapidly measure our conventional vital signs.
I just want to interrupt with a question that came through in the chat box.
Sure.
Actually, a couple of questions. The first one is, does body mass index or weight affect these the accuracy of these techniques?
So they would, at least for radar signals, they're not going to, lots of mass between like your lungs and your chest would slightly change the motion of your chest, but it's not going to change it so much that you would not get a clean signal. If for an extremely obese individual, I think we would probably start to have a really hard time with getting heart rate, because that mechanical signal would be damped, mechanically damped by the time it reaches, say, the chest wall or the external surface. But for the most part, body mass is not going to impact significantly these, at least the radar signals or the optical signals that are coming from exposed flesh.
The second question is, do you want to comment on use of these techniques during pregnancy or postpartum?
Yes, great question. So the levels of energy that we want to use here, in any case, you need to be fundamentally safe for the individual, and we're exposed in a safe way, in an approved, regulated way, to radiation from our Wi-Fi's, from our cell phones, on a fairly constant basis. And so the level of signal here is much smaller than what you're exposed to on a daily basis from the other RF signals that are in the environment. And everything is below the sort of the FDA's regulated standards of how much radiation you can be exposed to. The benefit here is that we, as opposed to being in an ambient environment where you just have the Wi-Fi signals or your cell phone signals bouncing around every place, we can use a very little bit of energy because we know where the person is standing relative to our sensor. And so we know that we're looking at them in effect. And so that makes it easier to use very low energy levels and to stay fundamentally safe for everybody in the population, not just pregnant or otherwise.
And one final question, and I'll let you go on. In the illustration in this one of the box, the individual is standing up. Is it possible to design a system that would be more vertical, so someone who's on a stretcher or in a wheelchair or otherwise disabled, you could also get their vital signs?
Yeah, that's a great question. And I think one of the other areas that I'm focusing today on this kiosk because it connects nicely to our operational needs with COVID. But some of the research that we're doing is how do we use these sensors in the home And a very natural place to put such sensors in the home is over the bed, or over a couch where somebody is now lying prone instead of standing vertical. And so absolutely, the same approaches are applicable with the body in multiple orientations. The main consideration, to make it maybe easy for the data analysis, is to have a little bit of knowledge about what you expect the orientation of the person to be relative to the sensor. And so you don't expect people to be, well, unless you have kids, you don't expect people to be jumping on your bed. And so you can expect that people are laying down in the bed. And so you have some prior knowledge about how you expect their body pose to be relative to the sensor. Or if we had things in the living room, for example, we would generally expect them to be walking through the living room or standing in the living room when they're not near a piece of furniture. So having some of that contextual information can simplify the algorithms in extracting the information that we want out of the data.
Great, thanks.
Certainly, absolutely. Thanks for asking. Okay, so this is now vital signs that we think of, the ones that when you go to the doctor, okay, we're gonna measure your breathing rate, we're gonna measure your respiration rate, we're gonna measure your blood oxygenation. But we also have to ask the question, what are the vital signs that are not standard, right? That maybe are a little bit more difficult to measure in the doctor's office, but that would be maybe a little bit easier to measure in the home environment or in sort of the context of daily living. Right? And so what are some of these maybe a non-standard or beyond standard vital signs? There's a lot of power, and I'll focus a little bit for motion, like how people are moving around. Right? You know if you're not feeling well, that how long it takes you to go up or down your stairs or to get in and out of bed changes. And so just if you had the ability to monitor your motion and how you move around, maybe how your arms are swinging or your sit to stand ratio from going from standing to sitting on the edge of your bed to lying down, there's information there about your health. Your physical strength in the home environment, if you are, you on a regular basis, you grip doorknobs or you grip handles, and your physical strength, right, will change depending on how you're feeling and how you're aging or if you're sick or not. And maybe not just your temperature, but your temperature cycles throughout the day, your daily cycles, your daily variability. So I think as a community, we sort of, the clinical community knows how to use the vital signs, our breathing rate, our respiration rate, and those things are measured episodically when you're at the hospital or at the doctor's office. But what does it mean now to move beyond those conventional standard vitals and getting things in the home or getting things that you really can't get robustly unless you're measuring them very frequently? Like it would probably not tell me much if I asked as a patient going into the doctor's office to measure your sit to stand ratio or how long it takes you to go from a standing position to a sitting position, measuring that once a year. That's not going to tell me much. I don't have any good baseline to compare that to. But if I'm monitoring my own motion in my own house on a continuous basis, and I suddenly see that it's taking me 2 times as long to get up out of my chair or to go up and down the stairs, that tells me something very powerful about how my personal health has changed. So I think there are these other vital signs, whether we're measuring them in a kiosk or in the context of the home or the workplace, that we're very interested in trying to understand and develop sensors and techniques to measure and quantify. So I'll focus just a little bit more on motion. And there's a lot of literature and everything from looking at Parkinson's disease to chronic obstructive pulmonary disease, where different types of motion, whether it be arm swinging in the case of Parkinson's, or in the case of heart failure or chronic obstructive pulmonary disease, looking at exacerbations or sort of the likelihood of being re-hospitalized, a very simple number of how long it takes you, your sit to stand ratio of how long it takes you to stand up or sit down. And that's changing significantly. That tells, it's been clinically shown in some preliminary research that is a very powerful measure for select diseases. and motion is a very powerful thing. And not just the motion of your chest or of to get respiration rate and heart rate, but your body motion. So going back to radar, we can now think about not just our chest wall, but all parts of our body as we're moving through a radar field or through a light field. If we have our face being a mirror and our arm being a mirror and our leg and our chest being a mirror, the way that we're moving is going to modulate the way that either radar or light bounces off our body. All right, so we transmit something, we transmit energy, it bounces off of us in various ways. And the way it bounces off of us is different, depending on what part of the body. And so, this is just sort of the framework where we can take all of these reflections as they interact with the body and do a bit of processing and characterize where those reflections are coming from, if they're coming from the chest or the arms or the legs, and then use that to extract information about our various activities. So what this raw data maybe looks like a little bit is this is a spectrogram where the axes of this color plot are velocity on the vertical axis and time on the horizontal axis. And what this is a simulation now of somebody walking across a living room, and we're getting reflections off of their chest, we're getting reflections off of their arm and leg. So embedded in this velocity versus time image is in this sort of center band is information about how fast the person is walking. There's information about how their chest is moving in response to their breathing rate. And up here in the tops and bottom is information about how their arms are swinging. So this gives us an image, if you will, of the motion patterns, and from which we can extract information about their gait, extract information about their breathing rate and respiration rate, so we can now expand the way that we think about the motion of the body to include gait analysis, arm swinging analysis, heart rate, and respiration rate. Right. So this is just a foreshadowing of what you can do now if you start to embed these types of sensing technologies in the environment around you. So the last piece that I want to share with you is maybe I should call it beyond standard vitals. And this is a work that was the PhD work of Sean Zhang, who's now a postdoc at MIT in my group. But this is sort of using both light and sound in a very, very different way, and not a conventional vital signs at all, but something quite powerful, I think, and quite unique. So to put it in context, we're still talking about non-contact measurements, and we're going to use light and sound. So first, some framing. I think many of you have probably received a conventional ultrasound exam. And if you go to the doctor, they'll hold on to an ultrasound probe, and they'll take that probe and they'll put it in contact with your body. They'll smear some ultrasound gel on the front face of the ultrasound probe to make good coupling between the probe and the patient, or between you and the device. And we'll acquire an image. And here's what some of these images may look like. This is of the arm, and so we're seeing the artery that's in the little solid box area, and we're seeing muscle tissue in the dashed box area. Now, some of the things that are added that are our research is this blue clamp. So as you can maybe imagine, when you're pressing a device such as an ultrasound probe against your body, you're simultaneously getting an image and you're distorting the tissue. So if I press really soft on my arm, for example, in this first image, if I press with 1 Newton, or sort of about 2 pounds of force, I won't compress the vein. Sorry, this was a vein, not an artery. I won't compress this vein very much. But if I press harder and harder, I can get to the point where I start to collapse this vessel. So how hard I'm pressing on the body will change the way that the image looks. Right? So that's not the main point of what I want to talk about here, but it's the physical interaction between the doctor and the probe and the patient fundamentally will impact the information of the image that you're able to see, and what the geometry of the structures, whether it be the muscle or the vessels that you're looking at. But I more use this image to say, here is what conventional ultrasound looks like. And it requires contact. It requires contact between the doctor and the probe, and it requires contact between the probe and the patient. So how do we make this non-contact? Okay, so I'll need you to sort of use your imagination here a little bit. I can take my finger and I can tap on my hand, or I can tap on a surface. That's a mechanical object tapping on another mechanical object. If instead I take a laser beam, and instead of it being a continuous beam of light, I turn the light on and off. Right? So I have a little pulse of light with then a blank space, a little pulse of light and a blank space, a little pulse of light and a blank space. And I shine that pulsed light onto tissue. When that pulsed light, this little red box is a sort of a frozen in time snapshot of a pulse of light. That light is going to be absorbed by the tissue. And that light is going to, for a very short period of time, heat up the tissue. And that heat is, and it's not, you don't feel it, it's not uncomfortable. That heat would generate a stress field, meaning the tissue wants to expand a little bit. And because it expands, it wants to propagate away that expansion. So it propagates away as sound. So if I now, instead of tapping, using a mechanical tapping source on my body to generate sound or to generate sort of a tap, I can take a pulsed laser beam, tap it on the body surface, and each time I tap, it's going to generate a sound field. That sound is going to propagate into the body. It's going to bounce off of things in the body, and then it's going to bounce back up to the surface. Now, that was generation. Now I need to detect. And there are a number of ways to configure, instead of pulsed lasers, continuous lasers. So we don't break the light beam into small segments. We just use a continuous beam. But we can, same way that we use a continuous beam of light to detect heart rate and respiration rate, we can use a continuous beam now to detect the motion of your skin, right? So this is a way to detect sound that's propagated into the body, reflected off of structures inside of the body, and come back up to the surface. So we put these two things together and make laser ultrasound, where fundamentally what we're doing is enabling the ability to get ultrasound measurements at a distance, so meters away from the person, where we use light to generate sound. The sound propagates into the body, it reflects off the body, comes back to the body surface, and then again we use light to detect how that body surface is moving. So completely non-contact, completely at a meters of distance away from the individual. So what that looks like in a laboratory setting first, to do experimentation. Here is what it looks like when we do it on a sample of tissue or of meat. The colors here, the yellow and the green are drawn to sort of make it clear where the light is, but you don't actually see the light. We have a pulsed laser beam, and then we have a continuous wave laser beam that is aimed at the tissue. And again, it's generating sound and detecting sound. And on the figure on the left is one trace, if you will, when the laser beams are at one particular location, and it's showing what the received sound wave looks like. And that sound, again, was generated by light and detected by light. It was only sound when it was inside of the tissue or inside of the body. And so we can see muscle boundaries and fat boundaries, and this air boundary is the laser was shining on one side. The sound propagates all the way through and hits the other side, and so this is a big air boundary on the opposite side of the tissue. If we then scan that laser beam across the body, we can then construct an image, right? Where we see now this is a slice into the body. This is an ultrasound image of that was never, where we never had contact with this piece of tissue. So that's with a sort of a piece of pork bought from the grocery store. But the exciting thing is, and this is a paper that came out last year in Nature, where it's the first completely non-contact laser ultrasound image, where here we see the laser beam shining on a person's arm. We see the muscle boundaries, we see the bone boundaries. And if we mechanically scan that beam, we sort of raster scan that beam across the body, we can now generate what is called a laser ultrasound image. And what is shown here is side by side, roughly in the same location, our laser ultrasound image on the left. So these are images that were acquired in a completely non-contact fashion, compared with what you would get with a conventional ultrasound probe where we're making contact. Now, indeed, the quality image is very different, right? There's been decades of work that have gone into making contact ultrasound systems be able to produce very sharp images and to robustly identify, here's the bone boundary, here's the skin boundary. But for the very first time ever to sort of generate a completely non-contact laser ultrasound image, we can see these boundaries that are indicative of tissue structure. Now, once you're able to do this, right, there's obviously a lot of work and research that we need to do to get to the point where this is clinically deployable, and it gives us information as robust as a contact probe. But as we think about this expanded nature of non-contact, both vital signs measurements and medical measurements in general, we're very excited by what this sort of laser ultrasound technology can do. And I think that's where the story that I wanted to tell today. Sort of started with the very simple of using thermal cameras to tell you a little bit about measuring external body temperature and how we're using that to support our COVID testing and tracking needs on campus. Talked about vital signs and how vital signs are currently measured in a contact way, to get you now then to think about making those same vital signs measurements in non-contact ways using light and sound and radar. And then also thinking about different types of vital signs, such as motion, and then wrapped it up here with sharing some of this sort of exciting new work that we're doing in laser ultrasound, where the image itself is a sign, is a signature of the tissue. And so instead of getting just a measurement of motion or respiration rate, we can say something about tissue structure or how tissue would be healing, and getting that in a very non-contact way. So with that, I'll again pause for questions, and I thank you very much for your time and attention today.
There you guys. Brian, first of all, I want to thank you. I think you did a really wonderful job moving from what MIT is doing now around COVID to perhaps the future that we'll all see, either in the hospital, the doctor's office, or in some of these techniques, even at home for people who need that kind of monitoring. It's pretty amazing. So now we're going to open up for some questions, and we have one already. Peter Ginsburg asked, how would you remotely listen to someone's chest for things like heart murmurs or chest congestion or wheezing or fluid in the lungs? Do any of these techniques help you with those sort of things that are part of a physical exam now?
Mm-hmm. So for passive sounds, some of those signatures, such as wheezing and congestion, some of them will show up on the skin surface, right? Because the same way that you use the stethoscope now, you're not listening inside of the body. You're listening to what the sound is that is at the skin surface. So as long as we're able to make our displacement measurements sensitive enough, we've not done this yet, but there's no technical limitation why we shouldn't be able to make our ability to detect sound sensitive enough in a non-contact way to be able to hear those sounds of chest, of wheezing or murmurs. And so, Yeah, so that's more of a passive sort of just listening, right? So you're just sort of you're detecting the motion, and in that case, we would probably recommend using a combination of light and radar. It's always better to have multiple ways to measure the same thing, but fundamentally, what you're trying to measure when you're looking at some of those sounds is sound is nothing more than motion at a very small scale, and so using all these things to measure that small scale motion should be feasible, although we've not done that yet.
Well, this could be a whole new world of telemedicine, I guess.
We have another question from the chat. And is there a technological reason that temperature non-contact scanning are not part of metal detectors or body scanners in the airport? Or perhaps this has changed since COVID, but can you comment on that?
The question was, why isn't temperature part of the body scanners in the airports?
Yeah, exactly. So like when you're going through the body scanner.
Right. Well, they're in the body scanner, they're looking for very different things. When you're going through security, for example, they're trying to detect whether you have metal objects on you. But at the same, so that's not part of what they're looking for in those situations. But on the other side in airports, for example, I used to fly in and out I used to fly internationally. I don't do that anymore. But you know, in Boston as well, if you're coming in an international flight, they will have thermal cameras that are greeting you in some of the entranceways. And so if you are sort of have an elevated body temperature, then the border security may pull you aside. And I'm not sure that's done in Boston, but certainly in places like Singapore, I've seen it. Many places in Europe, I've seen it, and I'm pretty sure it's in the U.S. as well. But it's more on trying to do detection of is somebody symptomatic? Is somebody have an elevated temperature, and to potentially quarantine them as they come into the country. It really hasn't been a need, I think, so far. And maybe this will change with COVID. You know, when you're going to fly, the body scanner would be a perfect place to deploy such a kiosk. Hey, it's your body scan plus your pre-flight medical vital signs measurement. But that's not been a requirement so far.
Brian, thank you. There was another question that came in. Why do you measure the temperature at the corner of the eye? So, you know, most of us, when you go to the drugstore, you can get a forehead measurement or behind the ear or eardrum, but how did you choose the corner of the eye?
Yeah, so it's a great question. This has been studied quite well. The tear duct is the most accurate place to make that measurement. And when you're doing it when you have the luxury of having an image and being able to identify the eye and pick that location to make the measurement, you can get a much more robust measurement than what you get with a forehead, because there's much more variation, and much more, I mean, sort of plus or minus a degree, but there's more variation on the measurement when taken on the forehead than when there is at the tear duct. And there's lots of literature on that. It's been a well-studied finding that is the most accurate place to take such measurements.
So, Brian, I think we want to just close by thanking you on behalf of the 4 clinical translational science centers in Massachusetts: UMass, Harvard, Tufts, and Boston University. And just to let everyone know, we've decided there will not be a call in September. There's so much going on with so many universities reopening and all of those things. So we're going to have our next one in October. If anyone is listening and has suggestions or things that they would like to for us to bring up, we're going to be returning to issues of, in addition to coronavirus, issues of health equity. And we plan to have some studies or researchers talking about vaccine development, the equity issues and the development and testing of vaccines. I know that's been in the news a lot lately, as well as other issues related to health equity during the pandemic. And I really want to thank you, Brian, for everything that you've done, for the work you're doing, for taking the time from your from your work to join us. And anyone who'd like to send more questions our way can email any of us, or just go to the Tufts CTSI website. And on the bottom left corner, there's a needs help comment. If you enter your questions there, we'll be sure to get them to Brian. Really appreciate everyone taking the time and attention today. And I hope you enjoy the rest of the summer. And good luck as we all go back to the next phase of our lives with school and hopefully, and everything else that the fall brings. Thank you so much. And a special shout out to Marguerite Fenwood for arranging this and doing all the work behind the scenes to make sure that we all had such a wonderful seminar. Thank you both.
Thanks.
Thank you, everybody. Thank you, Bob. Thank you, Maggie.